Good day, everybody, and you're most welcome to today's presentation for the Chappell Natural Philosophy Society. These are these alternative sessions which we hold fortnightly on a Saturday. They're devoted to fairly theoretical things in regard to physics or philosophical matters. And we're reverting today to our more traditional format in which we're looking at specific theories which are accepted in mainstream physics and maybe analyzing them and going through them with a fine-tooth comb. Last time we actually had James Arathoon who was speaking on the Hippocratic Oath. It was a rather philosophic type subject and its ramifications in regard to modern science. But today we'll be reverting more to kind. My name, if you don't know by now, is Ian Cowan. I come from Dublin, Ireland, and I'm moderating these sessions at the moment for my sins, or maybe more directly for your sins. But today, I'm pleased to say that we have a talk which I'm sure will be of most interest to all of us in Facebook, in YouTube, and also in the Green Room. It's called Incompatibilities with Special Relativity. Now, many of us here, I think, will be familiar with ostensible incompatibilities with the theory of special relativity. They could be with other experiments. You know, people have looked at other experiments, seem to fly in the face of special relativity, notwithstanding common, statements to the contrary. Paradoxes, illogicalities. I think it was Alfred O'Reilly who said that special relativity not only appears to be absurd, but actually is absurd. So we're familiar with this. But James Arathoon today, who's from Aberystwyth in Wales in the United Kingdom, will be dealing with how special relativity is, in his estimation, incompatible with the theories of measurement and dimensional analysis. So metrology and dimensional analysis, which is a powerful tool in physical science. Now, I just repeat something I said maybe 2 weeks ago, that James has validated with me the position that he takes with regard to these lectures. He doesn't mind in the least being interrupted. So although we do have a session devoted to questions and answers and more detailed discussion on any of these matters afterwards, and it could be half an hour, it could be 3/4 of an hour, could even be an hour, depending on how long James has. He certainly has an hour, and if he wants to take a good bit more than an hour, that's fine with us. But although we'll reserve the question and answer session to that, if anybody has an immediate point that he'd prefer to put to James now in the middle of his sentence, rather than wait till the end, just send a note to me and I'll bring you up, or I'll bring the point up and stop James. He's quite happy doing that. So it just remains to me now to bring James up, and I have to bring his slides up as well. So you're up now, James. Shall I bring your slides up now, or would you like to say a few words before that?
Shall I just quickly introduce it and then bring the slides up? Just a minute, just to say hello to everyone. The talk is slightly different title, but it's just a selling point. It's basically the same subject. It's I've called it Escaping Einsteinian Mysticism, because it's all about trying to spot. This goes back to the history of science, trying to spot implicit vagueness in what people have written in the past, and try and tease out some clarity which hasn't been seen before. That's basically the technique that Einstein used in the first place to establish his theory, and this is the sort of technique I'm trying to use again to demolish his theory. Anyway, it's called Escaping Einsteinian Mysticism: Why Relativity via Measurement Theory is Incompatible with Special Relativity, and it's a provisional progress update from me. And should we have the slides? Ian? Right. Okay. Right. So that's me. There's my email address for queries, and there'll probably be mistakes and stuff that you may want to tell me about, etc. So let's move on. So the basic plan of the talk is I'll just do a few introductory words. Then we'll talk about measurement theory. I'm not going to talk about Orthodox dogma, but I'll give you a list of things that are basically included in the indoctrination of students today in universities. And then we'll quickly move on to the main bit, which I want to talk about, which is relativity via measurement theory, which is basically a different way of looking at the topic of relativity. And then basically everything is just a quick conclusion after that. So. So rather than going on the different slides, oh yes, well we've done this one. This one's a bit small. So basically, my background in this area is I first learnt about Einstein's relativity in 1981-82 when I was 15, and that wasn't going out and buying a book or anything. It was just in a couple of articles in electronics and computer hobbyist magazines. So that sort of primed me. And then when I went to study mechanical engineering when I was about 18, I asked in an mathematical analysis about relativity, and the lecturer came back to me so harshly. Oh, that's not needed. You won't need to do that. He basically thought it not much of it. And it's sort of when you have these two conflicting things in your mind, one lot of people, the physicists saying how great it is, and then a senior lecturer teaching you mechanical engineering and saying something else. It's sort of that for me as a student, it sets a journey off, which is culminating today. So basically, when you get conflicts in your mind as a student, relish them, because they're your future sort of, perhaps success in life, although you don't realize it at the time. I didn't finish the engineering course. I did 2 years and then moved on to geophysics, and I wrote a dissertation on measurement of atmospheric conductivity, which is I've put on the Internet Archive some months ago, and that basically had lots and lots of waffle about dimensions and standards and all this, that, and the other. And so that was a precursor to this as well. That was in 1991, and I then studied for a PhD in atmospheric physics, which I didn't finish because I ran out of money. Although I did that for 3 years, and then I worked in the computer control industry up to the present time. I've had several, like many people in this talk, listening to this talk, I'll have several failed and extremely frustrating attempts to understand relativity, basically over a period of 30 years, not constantly, but every now and again when I've forgotten how horrible it was to try and learn it the previous time. Progress in my thinking along the lines of the present talk basically matured during the time of the pandemic. Right. Let's skip that one. I've just done a talk. This is an anniversary, because my mother was born in India. This is a Survey of India medal, and it's 1823 when William Lambton, the previous boss of the Survey of India, died, and he handed the reins over to Everest. So, hopefully, me at 56 struggling to learn and understand all this stuff can hand over to someone else who's got a younger, fresher brain. Anyway, so I've just put something which isn't relevant. So I've just say a quick word on the Socratic methods, because I haven't got any explicit or implied authority in giving this talk. So so don't go to your professors as students and say, James said this, such and such, is it right or wrong? Use the information provided, think about what it is, compare it with what you're learning, and flesh out questions and ideas for yourself. That's basically how you should think as a student. So, I mean, that's enough to say about that. I'll just read this because it's quite interesting. I've been studying the early figures that had thought deeply about dimensional analysis, such as Percy Bridgman, Norman Campbell, Frederick Lanchester, Alfred O'Reilly, Herbert Dingle, Julio Palikios, Louis Essen, the father of atomic time. Incidentally, if you look in Special Relativity books for the name Louis Essen, and his basic design of atomic clock is still being used, you will not find it. It's because he dared to question special relativity in the 70s, and he was cancelled by the professorship in our university. So he should have got a Nobel Prize, but didn't anyway. So as well as more minor figures. So one thing seems a common trait. They all had something to say about Einstein's theory of relativity, all apart from Lanchester, who basically was an aircraft engineer, were critical of the theory of relativity to some degree, with O'Reilly, Dingle, and Palikios being by far the most critical. Palikios was a famous professor of physics in Spain, based in Madrid. He was of similar stature to Dingle, because he came up with about a decade of tirades in Spanish against relativity in roughly the same way that Dingle did in the English language. So Bridgman thought it essentially correct, i.e. special relativity, and he thought the problem of understanding was just a presentational problem, which is a common theme. Norman Campbell tried to suppress his disdain for special relativity. Norman Campbell wrote early books on measurement theory, and nevertheless providing material in his modern electrical theory, together with its supplementary chapters for students to learn the practical applications of the subject. Lanchester had visited the home of Karl Runge in Göttingen, I'll spell that wrong, and personally met Minkowski in 1908, which probably accounts to some extent for his latter enthusiasm for Minkowski diagrams, space-time diagrams, greater than any engineer before or since, I believe. Well, I know, because no one has written a whole book on it. The reason I think that underlies this critical trend is the fact that the paradigm of thought required for taking dimensional homogeneity seriously as a concept does not easily fit with special theory of relativity, and has prevented some workers from generalizing the methods of dimensional analysis to encompass the theories of relativities in a way they wanted to or thought most natural. This was particularly true of Julio Palikios, who thought that dimensional analysis was incompatible with special relativity. Another philosopher, Lancelot White, made a similar point in his own way in his 1931 Critique of Physics. Right, so I'll try not to read like that, but it's just I just wanted to give you a history of the subject. So measurement theory, the word is typically used to denote the more philosophical aspects of measurement in science and engineering. But this is the talk I will use in this for purpose of this talk. This is the term I will use for the purpose of this talk because it more fits in with aspects of what I want to talk about. Dimensional analysis is a far wider term, and it involves lots of engineering applications of dimensional homogeneity, similarity analysis, modeling, control theory, all sorts of things that I won't talk about today. A dimension is simply an abstract or an abstraction of a fundamental unit within a standard system of units, such as the SI system. So we generally put dimensions, the abstraction of a unit, in square brackets like M, L, and T. I've put at the bottom there. So you have to know something about measurement theory, and particularly Einstein and Percy Bridgman. In the early part of the 1900s or 20th century, it was very, very popular to put forward positivist and operationalist theories, and they basically said if you can't measure it, it's meaningless, basically, or various ways of saying it. So that's one of the things I want to tease out, because we see lots of real things in the environment with real dimensions that have to be measured, and the dimension before you measure it is real. The size of the base of the pyramid, or the giant pyramid in Giza, that's real. It doesn't exist just because someone goes and measures it. So that's what I want to tease out. The measurement also exists, but in a different way, and there are differences between the real object and the measured measurement of it. So I've given some references to some of the key early figures I've been talking about. The book by Charles Focken in 1953 has quite a lot of good background, and it's more philosophical than many of the other books on dimensional analysis. Julio Palacios wrote a book on dimensional analysis as well, and he has his own unique point of view on that as well. Right, so the basic definitions, I know it's boring, but we'll just have to go through it. A physical quantity is any finite parameter attribute of an object that can be compared with a different instance of that same property or parameter object of the same or different object. So it's basically you're comparing like with like. Two physical quantities have to be alike. Two lengths you compare, to masses, to speeds, to accelerations. That's basically the name of the game. Physical quantities can be expressed as algebraic variables, then axiomatically assumed to obey the normal rules of algebra. And that's quite important in the ongoing. A unit is simply a type of physical quantity that is an agreed size, standard size or amount. By convention and to avoid confusion, units are defined as a distinct class of physical quantity that can only be combined algebraically with other units within the same unit system. Arbitrary physical quantities that are represented using algebraic variables are generally assumed not to be units unless otherwise stated. So, yes, so that's for the sake of clarity. And when you have a measurement, say the length of a table leg is 5 meters, the 5 meters that bit consisting of a number and a unit is said to be the magnitude of a physical quantity. So physical quantity is more abstract. So a length can be any length, but once you define the length, it has a magnitude. That's basically the idea. We all know about numerical numbers, obeying the normal rules of mathematics. Dimensions as well can be algebraically combined with other dimensions using multiplication and division only. So if you say if you calculate a difference of two physical quantities, like a bit of a table leg you want to cut off or whatever, when you do the subtraction, it still has the dimensions length, so the individual parts. So it only makes sense to combine the abstraction dimension by multiplication and division. Oh, this will be worth it when we got through all this. This is just stuff to basically. Standard unit is any amount of physical quantity. There's fundamental units defined, which basically are a small set of units which are used to define a whole range of other derived units. We can go back to that if you don't know. This is the bit I want to talk about. Now, the whole point of talking about units and physical quantities is to measure things. And a measurement typically involves a comparison of a physical quantity of a name type with the unit of the same type. So in this talk, I've put squiggly brackets around what I'm saying is a measurement. So a measurement can be a well-defined process, but it's basically a comparison process, and it will differ depending on the type of physical quantity you want to measure. But so that's an abstraction. It says, I want to measure a physical quantity, but I can only do it in comparison with a unit of the same type. So that measurement then produces a numerical value or number, and then we can write in the way I did before, say a table length, the physical quantity length, the measurement number, which is say 5 meters, and the unit, which would be meters. So 5 meters. So basically that's the structure, and that simplifies to the normal structure, which is physical quantity, numerical value, unit structure. Just to note, because I've seen it recently, and it's complained about incessantly in the literature. Do not write times numerical value times unit, because there's no algebraic rules for multiplying numbers with units. You just state it as number and unit. It might seem obvious they should be multiplied, but it's just like 5 oranges or something like that, or 5, anyway. The only reason I wrote that is because I bought a book from the IET, and the author made the same mistake. And that was quite a recent book, so people are still doing it. Right. The SI system units basically consists of a set of fundamental units from which all other units can be derived. This sort of represents, well, it's slightly changed now, but this is basically how they frame it still, even though the background of all this has changed. But so basically we consider length, mass, time, electric current, absolute temperature scale, amount of substance, and luminosity as the basic or the base units of the SI system. And then from those base units, we can calculate things like area, which I've put down, and the dimension is just the L to the power 2, and then there's volume, which is length cubed or meters cubed, and the dimension is L to the power 3. And so you can see that there's things of the same type are being algebraically multiplied out. So the three lets multiplied is length cubed. The units are meters cubed, and the dimension is L cubed. And for mixed units, a similar process occurred. So like density is a ml to the -3, for example. Most of you would know this. I'll quickly speed through it. There are many known constants, fundamental constants. The most relevant to this presentation is the speed of light, c, and since 1983 has been a defined constant. And the number I've given there is the definition. Just as an update, on the 20th May 2019, the complete SI system was defined in terms of various constants of nature, including the speed of light. But that is actually, it's not entirely by various constants, because because time is still defined by Essen's type of atomic clock. So that's time is the one aspect that can't at the moment define in terms of a fundamental constant. Anyway, that's beyond the scope of this talk, and so I'll move on quickly. These are the sort of subjects you get with the Orthodox dogma on relativity. This has been going on since Einstein first came up with his theory in 1905. You'll occasionally get references to ballistic theory of light, which is Ritz's theory, which although works well in the small scale and the laboratory, fails when it comes to observing binary double stars. So the ballistic theory doesn't work. What have I also put? You learn about Galilean relativity, which is everything seems to be relative in terms of motion and mechanics and everything. The stellar aberration from the ether point of view, which assumes you've got a fixed ether in a sort of Newtonian style. The Michelson-Morley experiment can be explained via the ballistic theory, but obviously that doesn't work in a wider sense. But you can also try and explain it using the Michelson-Lorenz ether viewpoint, but that famously fails, and that causes the whole reason for studying relativity in the further on. I'll carry it. Then comes Einstein's 1905 paper, The Concept of Simultaneity, stellar aberration from Einstein's point of view, Michelson-Morley experiment from Einstein's point of view, where there isn't any mathematics to it. It's just always equal path lengths. The Sagnac experiment is just a version of the Michelson-Morley interferometer experiment, which has a loop, an open center. So you basically can measure accelerations if you rotate the experiment. They don't typically explain that in student relativity books because relativity doesn't handle acceleration very easily, to put it mildly, and all the other things. And then came Einstein's prediction of light deflection and general relativity, which is not going to be talked about today. So just a few things. Right, now for the main meat. Does anyone want to answer any questions now before we? Is everyone familiar with dimensional analysis? And
yeah, well, if anybody wants to answer a question now to James, just put a note in the comments, or any in the green room, just raise your hand. We give you a moment or two. If not, we'll proceed.
Because you've basically set up now, and this is the main meat of the talk. So I just want to make, if you've got any questions that either you want to ask now or me to clarify as I move on, then say so.
They're probably happy to leave.
I mean, basically what I've said is uncontentious and standard sort of dimensional analysis stuff. Right, so let's carry on quickly then through this. So the idea of this presentation is to develop a real world model where mass, length, and time as unmeasured physical quantities, you don't have to put the unmeasured, but I just want to stress the point, change with velocity relative to a quasi absolute stationary frame. However, because both the physical quantity and the associated physical unit of the same time change by exactly the same factor when in relative motion to the stationary frame, the factor cancels out. So if you try and measure your motion relative to the stationary frame, because it's in this viewpoint, because it's consists in both elements of the comparison, it cancels out and you don't see it. So that basically this is the whole point of this talk. And right, so initially I'm just going to assume some things, and it'll become clear that this is consistent. I mean, I don't think there's another way of assuming these ratios. But anyway, someone might find another way, but this is the only way I've found. So assuming there's two inertial frames moving relatively to each other, they both start out with identical systems or systems of SI units and measurement procedures that were proved to give identical results in the same frame before the outset of the experiment. The ratio of the measured physical quantities, length, time, and mass between the two frames, K1 and K2, is assumed to be. Now I've put a little colon in because these are just notional comparisons. So this is the sort of thing which the operationalists were dead against, which was imagining two physical things in two different frames and their relative size, but they necessarily can't be measured to confirm that. So L1 is the length in one frame, L2 is in the other. So L2 is moving faster than L1 in general, but M2 is the faster frame, T2 is the faster frame. I don't know. We'll leave ballistic theory to later because I'm not trying to push that, and it's not accepted at the moment. So you can ask a question at the end on that. So so for length, I'm saying that so for the stationary frame L1, the L2 will be different by the factor of square root 1 over square root 1 minus v squared over c squared, and time, which can be verified between the two frames, that's the only variable that can be, is equal to the ratio given next to it, and that implies there is a ratio which you can't easily measure between the speed of light in the two frames. This is unmeasured speed of light. I'll keep having to stress that, because as soon as you measure the speed of light, you're comparing it with by a ratio, and you automatically get the same speed of light in all moving frames. And I'll explain that later. The velocity is exactly the same as the any arbitrary velocity is the same as the speed of light. And you can put v squared over c squared without putting a subscript, because they all cancel out and they're equal to each other as all factors cancel out, and so they're equal to each other. So this is basically saying that assuming, though, that there are differences which you can't measure, as soon as you make the ratios and measure them, you get to the bottom line, which is basically saying that when you measure the length compared to a unit length in one frame, assuming you've started out with the same system of units to start with, will be equal, or the same length will be equal, same time will be equal, the same. Basically, get the point that basically we're sort of assuming creating what you'd say as an unobservable framework from which the observed world is resultant. This is a common method because, and you have to choose your unobservables carefully. Otherwise, you get into, things like trying to find dark matter, which doesn't exist. Right. I won't talk too much about simultaneity, but in this sort of setup, you basically get a system simultaneity, or the mechanism is compatible with the method they use in the GPS system, although they have to take gravity into account for that system. But it's basically two moving clocks in the GPS system are considered to be basically different measurement frames, and they adjust the clock in the satellite to run in time with the Earth frame, and so there's a common system of units and standards common to the whole system, even though nature tries to run them at different rates. Engineers fiddle it to bring them back into line with the Earth-based measurements. So and basically this was the system that Essen was talking about, and everyone ignored him. But engineers have followed him and ignored Einstein. I mean, that's what's his name? I can't remember his first name, but Hatch has written a whole book on this and papers. So
Ron Hatch.
Ron Hatch, that's it. And basically, he died now, unfortunately. But he basically was telling people that the GPS system wasn't compatible with the relativity. I'm tempted to believe that it isn't, although there's plenty of people saying it is. But there we are. So there's Einstein's postulate. I won't read the ones at the top because there is the original text translated into English. AP French and other people, I've got the ones from the book French Special Relativity, which is a common student book, has simplified them as all inertial, postulate 1, all inertial frames are equivalent with respect to all laws of physics. And postulate 2, the speed of light in empty space has always the same value c. But now well, I'll try and answer the question. What we mean by value there. Again, this is just a positivistic system. So they're talking about measurement values, not physical quantities. So they're not talking about the thing before it's measured. They're talking about the thing after it's measured. And you basically, this leads to utter confusion when you try and analyze the situation. So in effect, because they're talking about the measured C there in the second postulate, that has now been turned into a definition by the SI committee. So postulate 2 is definition 1. Right, so this is where I talk about what I basically talked about. When you create ratios, you basically get rid of all factors from the physical, unmeasured physical quantities by creating the ratio between a physical quantity and the unit of reference. And when you do this between frames and then compare the results, you will end up with, as long as they were the same at the start before the frames separated, you will end up with identical results when you communicate them across CB radio or space radio, wherever they say they call it in space when they talk to other spacecraft. And so, and so all the things are basically ratios, measured ratios, and the relativity factors disappear. In taking the point of view I'm trying to take, this postulate is vague because there are two ways of looking at laws, i.e., unmeasured quantities, physical quantities, or the actual physical magnitudes, the measured magnitudes, and basically, since Einstein and Bridgman, we've sort of got into minds that only positivistic philosophy is right, and that all we need to talk about is measurement, and talking about anything else is meaningless. So the postulate, I mean, I've already gone through this. The same for the speed of light. So in my system, the postulates are basically, as long as you take the fact that they're these set of parameters which change unobservably when you do the maths, and the postulates come out of the wash as if by magic. I won't dwell on this, but the nice thing about taking a measurement theory viewpoint is you can further analyze things like clocks and things like that from a dimensional analysis point of view, because there is a certain amount of homogeneity in the relativity factors in the whole process of this. So, and this is what I tried to do as a student. You know, I was thinking about clocks because Einstein clocks are simple, divine, elemental, time-giving entities, as I call them. No structure, but every engineer knows that you have to work hard, especially Lewis Essen, work hard, be extremely talented to create a clock that works well, especially for measuring very, very small intervals of time, and to remain stable over long periods of time. So, I won't carry on with that, but get the idea. You can talk about not just the time period, the relativity factor, the mass, the relativity factor, but then the spring constant and all the variables that don't come out wash, like the acceleration and the velocity. So, well, I mean, some things like action, for example, that's a good example, which is mass times time. Yeah. Is it action or length times time? I've just had a brain. Well, length times time. The length times time, when you measure when you multiply those two, the relativity factor goes away. So it's the physical magnitude or physical quantity, is independent of the velocity of the frame relative to the stationary frame, which could be the CMBR frame, for example, the fixed frame of the cosmic background radiation, for example. I'll just quickly put it. Right. When you look at the Michelson-Morley experiment, in any frame, you get a null result. And in the normal analysis by Michelson and Lorenz, they basically have the experiment stationary, and then they point an ether wind coming through the experiment. So even before they start the analysis, they've done a transformation, because we're not in the stationary frame. The light is supposedly traveling in the stationary frame. So they've already done just to confuse students. They've already done a frame swap, and the confusion just carries on after that. But the basic scenario is you can't make measurements in two frames. You have to choose what measurement standards you're having in this view, that is. So you either choose the stationary frame to make all measurements, or the moving frame to make all measurements. You can't do a mixture, otherwise you just end up with a mess. So in my view, the Michelson-Morley experiment is just trivial. You end up with when you do the calculations, the set of relationships that I started assuming in the first place. So,
James, would you forgive me if I took literally your very kind invitation to interrupt you at any time,
yes,
even the most particular? I seem to have an urgent request from Denny. He's put a comment in. I don't know if it's due to some comment I put into the general chat, but I'm going to bring you up, Denny. It obviously is related to what James has been saying just now. So
yes,
what's the point?
the MMX did detect a slight ether drift, about quite a bit smaller than expected. And then the Dayton-Miller experiment at higher altitudes that followed also detected an ether drift, although not as big as they had originally predicted. And in fact, I have a book here somewhere. I mean, what's that?
Okay. Can I give the? Are you listening? Can I give the because I have looked into this. Give the proviso that it doesn't if the Michelson-Morley or the light is traveling in a vacuum, because there's certain discussion about whether they because if you have a gas that there may be some like the fizz effect, you get some things going on. So
Like a drag.
Yeah. Anyway, most people say there isn't a measurable effect in Michelson-Morley experiment, and in my simple view, that I haven't got one. So that may be different. There may be other little complications coming in, but so this the basic theory is that agrees with the current theory that there isn't an effect, and it's trivial why there is an effect.
So shall we work on that basis for the moment? And Denny, maybe at the end of the talk, you could raise this again in more detail. Would that be all right?
If you find the reference, Denny, by the time you I finish, then we'll talk about it.
Okay.
I'll note it down as well and have a look at it.
Thank you very much.
So I've put the so in the bit that says frame 2 moves in frame 1, the two double bars move in 3 locations, and so basically the experiment is moving through a stationary ether. So the light I'm just showing one ray, but generally when light travels out, it sort of goes out in a cone. So the light that's heading out into an angle hits the moving interferometer at 0.5 and then lands back again at the 0.9. And so contrary to the Michelson Lorentz analysis, it's the path length in the stationary frame that's longer than the path length in the host frame, or where you're doing the measurements. I mean, that's obvious. You can only measure that as the length it is, and so it's moving through this notional stationary ether, and the light path has to be angled in the stationary frame to get a strict up and down in the frame 2. So basically, the whole theory has been wrong right from the start. Even with Lorentz got it wrong because they did this swap around, thinking there's an ether wind, and it sort of confuses the whole issue. I don't know why. So basically, I end up with 3 relationships, which basically, in the terms in which I'm talking about comparing physical quantities, I just ended with a colon, meaning a ratio of one to another. So So when you do the maths, I'm not going to do the maths of the Michelson-Morley. I've done it so many times, and everyone else probably has done it so many times. But you can do it again. You get these relationships, which aren't really measurements. They're just a relationship between one frame and another. And they have to consistently agree within the set. So this set is the same as the original set I chose to define, and they're consistent. Right, a note regarding the derivations of the Lorentz transform. Basically, the Lorentz transforms are utter garbage. So they're derived in the most common way by taking the light sphere in two different frames and equating them. Now, Lorentz, in his documents, puts a k in there and then hastily sets them to 1. Einstein didn't even bother putting the k in there and assumed the 1. Now, in my measurement theory, x has a certain form, and if you have x squared, you have to put have to set the k to the square root of 1 minus v squared over c squared. So basically, you get a factor k as 1 minus v squared over c squared, and that is dimensionally consistent then in this theory. I'll do that on the next page. So I'm proceeding with the traditional approach of putting k1, and you end up with these Lorentz transforms which mix up space and time, and have caused all the problem ever since. You get reverse transforms, which I put there as well. Right. So now this is the transforms that I produce, and basically the idea is that all lengths of the volume contract by the same ratio. So the volume contracts as a whole, not just in one direction. And the time is a simple, basically, relationship without involving space. So that I won't go into the details. Easy to calculate. The inverse transforms are just the inverse. You've just got to put a plus on the Galilean part of the transform. So there's no mixing up of space and time, no distorting of frames in the direction of motion, there's all this rotational stuff as well going on. No twin time paradox nonsense. Nicely to simplify Galilean transforms as V becomes small relative to C. Well, that isn't true for the existing transforms. And this is compatible with dimension analysis. Right, I ran out of time, but it's easy to combine these transforms as you would the standard transforms, and so you can see the results for yourself. You have to do it for the physio experiment, for example. Right. I haven't been the first person to try this. So in 1961, Jose Alvarez Lopez, who's famed for writing books on Atlantis, and after he had a very, very technical career in Cordoba, Argentina, studying general relativity, he moved on to more esoteric books on pyramids and all sorts of things, keeping a measurement sort of focus, but haven't read them because they're all in Spanish. I'm learning Spanish, but it's just taking time. So he was a mixed character, but he had a initial career where he studied general relativity and stuff, and he I haven't fully understood exactly, but it's linked, but I haven't fully understood it. But I give the name because he called his system relativistic dimensional analysis, and it's if you search for his name and relativity, you'll find it on the web. Someone's uploaded to what's the archive beginning V? The Crank archive. It's not the normal archive. It's the Crank and Visionary archive, where you can't get published on in existing media. Anyway, they put it there. So the ideas can be extended to Maxwell's electromagnetism, which I haven't worked out in detail, but I've given a few indications that there are consistencies. So it's known that charge doesn't change relativistically, but what I'm saying, it's not charge that doesn't change relativistic. It's Q squared over epsilon, the permittivity, that doesn't change, and also currents don't change. When you notionally compare physical quantities, this is unmeasured things whenever I put the colon. So the permittivity changes, the permeability changes, force changes, mass changes, acceleration changes. Yeah. So the assignment for students is compare and contrast part A. I haven't given it, but you can find it in the standard textbooks, with part B presented here. Discuss your thoughts, ideas, definitions, deductions, and conclusions with your fellow students and teachers. I.e., don't bother me, because I'm not being paid to teach you. Right. Oh, I'll leave that. So to conclude, this presentation is given freely and help promote further thought and inquiry. It's more conceptual, so you might have to take a little time to realize that there's a thing called unmeasured quantities and a thing called measured quantities, and they have different properties. And people like Einstein mixed up the two quite freely. In fact, all physics professors today in theoretical physics probably don't really know anything about dimensional analysis. It's mostly used by engineers and experimental physicists. So the talk is of a very preliminary, incomplete nature, and referencing to past academic literature is limited at the present time, although I've given you a few indications of what's been done in the past. I apologize for any errors, mistakes, typos, and I'm currently researching the history and philosophy of the subject, but it's a slow going, as it can only be done as time and financial resources allow. There's a book covering the history of measurement and dimensional analysis by John Roche. It's called The Mathematics of Measurement, A Critical History, which is very interesting. So if you're still awake, please comment and questions. Thank you.
Well, thank you very much, James, indeed. I omitted to mention that when I was discussing with James some of the presentations, we had originally planned for today a talk on James's contention that basic Newtonian theory of gravitation can be derived from first principles, physical principles. But we decided that this would be a better talk, to start his more fundamental analysis of physics, and in particular questioning fundamental physics today. And I don't think we've been disappointed. I think hopefully the Newtonian talk, James will be able to come back to us in the autumn and give us that. But quite a number of...
James Keane has asked, How do you know a frame is moving through a stationary ether? Well,
okay. Well,
you
could I
basically
just
can
say a few
see-
more words, and then we'll come back. In fact, as James
Oh.
is on the in the green room, perhaps we'd ask James to come up and give that point himself. So shall we just do that? Just give me a moment, please. Okay, thanks very much, because I'm trying to look at the general comments from the social media and the private chat. So that was an earlier comment of James. Yeah, okay. I've only two comments, maybe just before handing it over to the more general discussion. I was interested actually that you, James, had referred to the Sagnac experiment, and if you look up the Google, the explanation, the Wikipedia, and all these things, they basically explain it away by saying what it concerns acceleration, and SRT doesn't concern acceleration.
That's rubbish. Yeah,
it's rubbish. Exactly. It's quite
because as I said, the ballistic theory handles it perfectly well and consistently within the philosophy of that theory. I'm just saying that it's a nice theory, ballistic theory, but it fails when you make a remote observations of stellar objects. So, theories have to just work well, not just in the Earth frame, but for all observations so it's a nice theory, and you want to try and get a theory as simple as that one to work for everything, which is what I'm trying to do here.
Okay. Now the other thing is, just one question. I may just take the moderator's privilege by just asking you one question, and then we'll hand it over. You said laterally that according to the conventional theories, charge is taken as invariant. Yes, but I think you also said that current is as well. But surely, according to the conventional theories, current wouldn't be, because time enters into the equation. It's charge per unit time.
I put in my right. So if you by the question mark, you say Q2. So in my theory, strictly speaking, charge is not invariant. But what is invariant is this Q squared over epsilon, which is which basically you always get that in all. For example, if you the classical, when you accelerate an electron, for example, the mass increases, and you can do a classical theory to particularly increase in mass, and you always end up with the factor Q squared over E. So in fact, the mass increase in a classical theory in that case, because that component is invariant, is solely due to the fact that in my model, the radius is reducing. So the length varies relativistically inversely to mass, which is what we see. So that is consistent with I'm not saying the classical theory is correct, but the indications of that is the way to go, and that is this theory is consistent with that. So basically, you can think of mass as being 1 over r.
So would it be fair to say that your analysis would be nearer to something like Lorentz ether theory, in that you're accepting these dilations?
Yes, because basically, to answer James Keen's problem, you can see the a stationary ether in effect, because you can see the fixed frame of the cosmic ray background, cosmic background radiation, and when the Earth moves around the sun, and the sun moves in the galaxy, they move relative to that, and we see a Doppler shift in the sky, which they have to cancel out before they can get the nice pictures they display on the web. In fact, the recent measurements of cosmic background radiation, are so sensitive they can't even measure that Doppler shift anymore because they have to cancel out in advance. So by tuning the sensitivity. So
I must say, I'd like to bring up
so currents in my system are exactly from a physical quantity point of view are exactly invariant, but charge isn't, and it's only in the. So if you could find a way of measuring charge without getting epsilon involved, then this theory would predict some invariance. I don't know how you do that. I don't, because you don't normally separate the q squared from the epsilon, because it's basically that's how. I mean,
the dielectric constant, maybe, just more general. Yeah. Okay. Well, I notice a number of people are in the green room, and I'd like to get all their views, and maybe James, can discuss this question of his in more detail. But just prior to that, I'll just scan through the comments. I've been doing that as the talk progresses, and I've been trying to answer a couple of them. But I think maybe some have come in recently, which are more specific for you. So I'll just maybe look at those. See, is there anything there?
This is not just thought experiments. What I'm saying is there's a background of stuff you can't measure, so unobservables. This, the sort of unobserved, and those unobservable structure then leads to what, once you do the calculations, leads to what we see. So this happens in all theories. You have to basically say, for example, Newton's theory, where he says a body will carry, if you give momentum to a body, it will carry on indefinitely. So that involves assuming that friction doesn't exist. Well, friction exists everywhere, so that is an abstraction. That's sort of an unobservable. Even when you get super fluids and things like that, they're so contrived because you have to keep them cool to keep the superfluid situation going on. That I suppose you could say that was a example where all friction is lost, but you have to input so much energy to maintain that situation. It's not really relevant to. So effectively speaking, there are lots of things in all sorts of theories which are basically unobservable. There are metaphysical elements to all theories, and I'm just trying to say that in this one, when we observe lengths like the height of a tree or something like that, it exists as a concept that enters into dimensional analysis, and then we have to get a unit to then measure it, and then it exists as a different entity, i.e. a number and unit combined. So and that measurement then has different mathematical properties to what that's basically what I'm saying. It's not just a thought experiment. It's a valid way of looking at things.
Okay, so I think that was James again. So really, as far as I see in the short presentation today, the short time we're available, we have to see whether you have convinced us, James, the people who might be largely sympathetic to critical thinking in this area, whether you've convinced us that there's a fundamental incompatibility between dimensional analysis and special relativity. And also, do you think that, or do we think that you would convince the mainstream? Now, I've gone through all the comments, and I think we can leave those for the moment. So I think Denny, again, was waving his hand a moment ago. And
all right, let's talk about the Michelson-Morley.
I'm going to bring him back. Denny, you're back now.
Thank you. This is I'm going by this book. Can you see it? In the Grip of the Distant Universe, The Science of Inertia,
who's this by
Peter Granow and his son Neil Granow. Peter
Okay.
was at MIT and then later at Northeastern. Now, as I mentioned, after the Michelson-Morley experiment, there was another set of experiments by Dayton Miller. Here, I'll read it, the key factors here. The most thorough set of experiments was performed at Mount Wilson, in other words, at high altitude, between 1925 and 1926. In this period, he took over 100,000 readings from 6,402 turns of the interferometer. The readings were taken in 4 batches separated by 3 months to investigate the effect of 4 epochs of the Earth's orbit around the Sun. In comparison, the original Michelson-Morley data was taken during a single 4-day period involving only 36 turns of the device. In addition, Miller had taken the previous 2 years to perform control experiments, which involved subjecting his apparatus to known mechanical and thermal distortions so that such effects could be eliminated from the final experiment. And then he gives some references. In order to appreciate the magnitude of the Miller discoveries, it is necessary to understand one astronomical concept, that of sidereal day. A conventional 24-hour civil day is the time required for the sun to repeat the next day at the same east-west longitude. This is the day that we measure on our watches. In this time, however, sidereal time, the Earth has completed a small, in regular time, the Earth has completed a small portion of its orbit around the sun, and consequently at midnight, the sphere of background stars that we observed has rotated by a few degrees from the previous midnight. The amount of civil time between the reappearances of the fixed stars in the same location for a given observatory is 23 hours and 56 minutes and 4 seconds. This is a definition of a sidereal day, which is split evenly into sidereal hours, minutes, and seconds. In other words, the sidereal time is relative to the fixed stars and hence relative to the ether, if there is an ether. Miller reported in 1925, after analyzing the data from the first 3 epoch periods, the curves of the first 3 epochs were simply averaged, and it was found when plotted in relation to local civil time, the curves are in such phase relations that they nearly neutralize each other. The average effect of the 3 epochs was implied, thus plotted as very small and unsystematic. The curves of the observation were then plotted with respect to sidereal time, relative to the fixed stars, in other words, and a very striking consistency of their principles was shown to exist not only among the 3 curves for azimuth and those for magnitude, but what was more impressive, there was a consistency between the 2 sets of curves as though they were related to a common cause. The average of the curves on sidereal time showed conclusively that the observed effect is dependent on sidereal time and is independent of diurnal and seasonal changes in temperature and other terrestrial causes, and that is cosmical phenomena. And here's the plot. You see the there, yeah, on the left. If you plot versus sidereal time, then you get a nice sort of a sine wave. If you plot for the civil time, the usual time, which is not relative to the fixed stars, you get essentially a confused nothing. So that was the whole problem, is that they didn't realize that the situation was so delicate, they had to use sidereal time relative to the fixed stars.
So have you any response? I think this is basically Miller's experiments, and actually they were later on explained by that pupil of Miller's. I've just forgotten his name. Contrary to what it says in the book, and Denny quoted,
yeah. There was a big
temperature effect and so on.
There was a big review published in the Physics Reviews, and it basically went into it.
That's right.
But there is I can't really find it now, but there is a guy who's considered a crackpot, but he's, there we are, everyone's considered, who basically says that there may be an issue with doing this experiment in a vacuum compared to doing it in a gas filled environment, and that may be something to do with the fact there is changes in the gas as we rotate around the sun, etc., like that. But because people haven't studied it, with various gas pressures and whatever, none of this, because as soon as you start doing it with changing the parameters, you can instantly see whether there's any. Because if the effect is increased with higher pressure gas, then you'd instantly see something. So
well, yes,
it's an open question. It's still an open question because the small effects matter, and we've been looking for dark matter, which is a null effect for donkey's years. People should follow up small effects a bit. We shouldn't just accept that 80 years ago someone wrote a report saying this doesn't work. Someone should perhaps double check again. That's my view anyway. So yes, unproven but interesting, I would say.
And by the way, this Grano and Grano's book and Newtonian electrodynamics, we're planning to have a presentation later on in the year on that by Boer, by I think it's Jim Boer. So anything else you'd like to say? Do you want to come back on that, Denny, or is it something we'll have to park for the moment?
Well, he mentioned if the gas pressure goes down, the readings may change. But that could also be interpreted as, since it was a high altitude experiment, could be that the Earth drags the ether more. The closer you get to the surface of the Earth, the more the ether drag. And the further, like on top of Mount Wilson, the further you get away from the center of the Earth, the less the ether drag. So it could be interpreted either as a gas pressure thing, or
when you have gas involved, you have to keep the temperatures very, very stable and eliminate all the. So it's not an easy experiment to do with gas. That's why most people do it in a vacuum now, and so any effects of the gas, having the gas there, will be, unknown effects. I should say.
But nowadays, if you don't get the right answer with your experiment, you get canceled. Whereas in Dayton Miller's time, that wasn't true. Although after he died, a lot of his data mysteriously disappeared. But it wasn't quite so bad then.
I mean, he was certain he found the effect, but other people reviewing it, until someone decides to reopen it, it's sort of an open question, I suppose. Because there may be a small effect.
Well, certainly, I think I, in common with many other people who've studied this in their younger years, never came across this. And the only thing I came across in one of the undergraduate textbooks was what you referred to, James, a moment ago, the analysis in 1955, and that some lingering doubts have now been put to rest because there were some experiments. It didn't specifically say Miller. And that will,
but it was basically a paper job, wasn't it? It was it wasn't. They didn't initiate a new set of experiments to double check or anything. They just reviewed what was available. I haven't I mean, I have got the thing somewhere on PDF, but I haven't really looked at it in detail. The review that was made to discount the evidence that Miller produced. But
Well,
I find
they say what they know their audience wants to hear.
yes, and because things like dark matter, which everyone sensible can say it doesn't exist, they're still trying to measure it on Earth, and
Well, there's a lot of money in it. You get promoted, you can become wealthy.
And it's a bit of a vicious circle.
It's not saying that, but it's that there are sociological effects which keep these things going.
Some scientific points are put forward for various reasons. Maybe they're believed to be true, and then they become accepted by people, and then that comes back and influences the scientists or the scientific people or the media to express points which are consistent with those points. So it is a bit of a vicious circle. Indeed.
I mean, I had in my dissertation, which on atmospheric conductivity, which I put on the archive. This happened to me that basically measuring atmospheric conductivity. You just have a tube, which is basically a capacitor, which you pass through air, and it measures the ions by putting electric field. And one guy, I was doing this at Lancashire University, said, "Oh, we had some strange results when we used to demonstrate this equipment because I rebuilt it for the purpose of my stuff with modern circuitry." But he said we had some strange effects because when we used to light a match or something anywhere near it, we used to get the thing used to go mad, and then I thought about this in the back of my mind, and then realised that it's a DC device, i.e., measuring the slow change of ions in the atmosphere, also is can accept AC signals, i.e., very fast changes. And then I did all the calculations and realised that this was both the DC effect and an AC effect, and they are different amplitudes of what you should expect. And as it happened, this happened on where I was measuring it because I don't remember his name, but there was a guy in the environmental science. It was a complete disaster. He caused fires and all sorts of things. Anyway, he as part of his PhD, he started laying out, coal tar residue from when he used to make gas from. He laid this out on the ground just in front on the last day of my experiments, and my apparatus went haywire. It's basically as all the volatiles evaporated from it, it created iron, and it basically. Anyway, I had a chance to verify that this sort of quick changes going through so the instrument had been in existence for 100 years, and no one had, even a simple instrument, recognized that there was another way of looking at things. So this happens all the time, and people should be more open to ideas, because there's always this little discrepancy that turns into a major discovery scenario sort of situation.
Okay, well, if we could perhaps leave it at that, and I'll bring up, I want to bring James Keane up next, because he made a number of points. I just want to make sure that James Arathoon has covered them. So if that's all right, Denny, I'll thank you very much for your contribution. If you want to come back, of course, you can do that. So James or Jim, just to make sure that your questions were answered, and if you want to add anything, please feel free.
Hi, James.
Okay, thank you. Hello, hi. Thanks for your presentation. Very, very interesting. I particularly like the part about requiring operational definitions of concepts in work in science. Let me start with a question, and then I have a couple of points to make. The question is ether defined as the stationary frame? Is that how you define ether?
No. From this perspective, there isn't. a definite ether as such, because all I'm saying in this is that you can define a frame and discover whether the frame definition is going faster or slower than the measurement. So, but there are ways of thinking about zero or stationary frames.
What does that mean? Going faster or slower than your measurements? What does that mean?
Either the time runs faster or slower, and it's in my theory, it's a easy reciprocal relationship, not one involving space mixing up with time. So if you compare the clock, so if gravity wasn't involved with GPS and the satellite was moving around the Earth and the clock runs at a different rate, you can then say, well, if the clock runs faster, I could forget which way around it is, and I've been going too long. It's either going faster or slower, depending on whether the clock's running faster than your frame.
It goes slower if it's moving, and with the gravitational slower around.
Yeah, I'm sorry, I'm getting brain fade with my.
Easy.
So it's so from that point of view, we haven't got a stationary frame, but we can know. And this is the whole point of the twin paradox. It's very difficult in the standard scenario to decide what makes sense of either a frame going faster or slower than another, because the Lorentz transformations are symmetric, and you have to work hard to find out how you discover that there's an asymmetry is involved in normal measurements. Anyway, to get back to stationary frame, in fact, when you have a gravitationally bound system, the center of the mass so they can be moving chaotically or rotating nicely, like in the solar system. The center of mass of the whole system is always stationary relative to all the other. So that's one way, if you can calculate the center of mass. Now we can see the cosmic background radiation, microwave background radiation, I should say, and on that background is a Doppler shift, which varies as the Earth moves around the sun. And so that is effectively a fixed frame. And I think they've tried to work out where the fixed point is, and it's somewhere in I don't think it's in our galaxy, it's somewhere in the galaxy group, so of our local galaxies. So that may coincide with the center of mass of the whole system. I don't know, and that's a hypothesis, but it would make sense if it was. So there are now. The trouble is that galaxy groups which aren't gravitationally bound are moving apart as the universe expands. So every galaxy group will have their own stationary reference system from that point of view. But if you think about it, the stationary system may be the clock running in the stationary system in one galaxy group may be the same as the So I don't know. I'm trying to think this through. It's quite complicated, but so it's not like Newton's system where there's a universal zero frame. We have lots of zero frames, and it depends on the galaxy, on what we can see of the cosmic microwave background radiation, and whether we can determine.
Is there experimental evidence for that? Is there any experiment? Sorry to interrupt, James. Is there any experimental evidence that there are multiple frames? You just said. or is that just speculation?
Well, the only way of doing it is if you could verify that there was a certain type of pulsar, because pulsars produce very, very regular.
Multiple.
Yeah. If you could verify that there was a certain type of pulsar which always produced the same frequency, then, perhaps. I mean, they do that. They do it with absolute candles for measuring the cosmic distances. The certain types of supernova produce a certain exact amount of light, so you can work out their distance from the 1/r squared effect. So the only way to verify it would be to have be able to look at clocks like pulsars in distant places. But within our galaxy group, there should be no reason why we can't find out where the stationary point is from a center of mass point of view, if you get enough work and enough observations, and and enough will to do it.
Yeah, unfortunately, the philosophical predisposition still comes into it. You have people getting the same experimental data and drawing different conclusions. So, but James, is there anything else you want to?
Yeah, well, I'd just like to go ahead.
So nothing I've said here allows you to. I mean, this basically agrees with Einstein's contention that you can't tell if you don't observe anything outside your frame and you're in an inertial system. You can't tell how fast you're going, because when you make measurements, as I've said, you have to take the ratio of physical quantities, and then any factors which would give away your speed relative to a static reference frame are cancelled. But I'm saying that even though they're cancelled, there is a static reference frame which light travels in, and when you do the calculations in this method, it basically says that any frame can be considered a static frame, because those factors which would identify the static frame cancel out. So I hope that's clear. I'm trying to be.
Presumably, any inertial frame.
Any inertial frame, yes.
Yeah.
So,
but of course, as has been pointed out in the comments here on the social media, that's basically Galilean relativity.
Yeah.
Nothing
but
special.
This thing with not being able to take acceleration, I mean, I think that identifies that the whole theory is wrong, because Newton theory you can calculate acceleration quite easily, and with this you can accept acceleration. With Ritz's theory, although it's wrong, you can accept acceleration easily. So even if what I've said isn't right, I hope people will think about the vagueness that I'm trying to identify and what's being said, and whether the dogma of what you can't measure doesn't really matter is correct. I mean, that was the dogma of Bridgman and Einstein and all the people in the early part of the 20th century. I think it came from Ernest Mach, because he was, this relativistic philosopher.
Actually,
I might be able to emphasize your point, James, even more by saying and throwing out, just for your consideration, that I consider that light speed is not a so-called fundamental constant of nature, but is in fact an unexplained observation. And all of the equations on all of your slides include C, the value of C, this unexplained observation. So that a lot of the so-called relativity theory is really more unexplained stuff, okay? Because C, an unexplained observation, is used in all of it. I might liken this, in conclusion, to trying to master calculus before you understand and know the basics of algebra. The basics of algebra level would be to have some explanation of why the measured value of vacuum light speed is what it is, and we don't have that. So that then trying to use this unexplained observation in all of these equations in special relativity, with the v1 minus v square over c squared, the square root of that in all of this work is just more unexplained stuff. So I'll leave you with that conclusion if you care to comment on that. My own work in binary mechanics, to end my comments, does derive the vacuum speed of light without using any unmeasured observations. And so that's sort of where I'm coming from there. Thank you for your attention.
So if you could be as brief as possible, James, because time is running out and I want to bring one or two more people in on the green room.
I'll just quickly comment that science makes progress when people understand fundamental constants or reduce the number.
So you agree?
So not necessarily with your theory, but yeah, the sentiment and the direction where you want to travel. Yes, I do.
Yes, that's what I meant.
Yeah.
Oh,
Thank
you. Well, thank you very much, Jim. If we can leave it as that, that for the present, I know we'll be coming back to a lot of this. Thank you very much indeed. Harry, whose camera is on, I see Eric and Cornelius are here, but they've no cameras. They might want to put the camera on in a moment. Harry's asked a couple of questions, and I think importantly, Harry, who's looked at this subject in great detail, is not convinced by your theory. In fact, maybe he's not even sure how you're coming to this. So, Harry, perhaps you could just elaborate a little on your two comments into the private chat. Is it true that you're
okay?
Bit of a delay.
Okay. In the past, my computer doesn't work very well. Do you hear me?
Yeah,
do you hear me?
I can hear you now. I think there's a bit of a delay.
Are you saying that Einstein's principle of relativity is false?
I'm saying it's only true for measurements which hide the true nature of reality. So when you try and make an analysis of physical quantities, before you've divided them by a unit, the factors will be there. But unfortunately, you can't measure that. But only if you consider the hidden structure of reality will the theories make sense. And as soon as you create the divisions, i.e. the measurement, the principle of relativity falls out as just an obvious statement, and the speed of light being constant falls out as being an obvious statement. It's not relevant to creating a understandable theory of relativity. It just, if you think in terms of measurements, you can't think properly in terms of understanding the world. That's the point I'm making. So it's both right and wrong. So I say there's a hidden vagueness which has led us to all this confusion and nonsense and mysticism and utter waste of time we've had over the last 50 years, at least, since Dingle, was
okay. I'm not really sure what it is that you're saying, and I guess I think Ian already brought that up. I'm not really sure what the conclusion of this presentation is. Are you saying? I'm not really sure what the conclusion of the presentation is. I thought you were saying Einstein's principle of relativity is false, and that was a definitive conclusion, and now I'm not so sure. So I'm not so sure what your conclusion is. Can you sort of explain it to us more simply as to why you think relativity is false because of a theory of measurement?
I said special relativity is wrong, not the principle. I mean, the postulates of relativity, i.e., all measurements in inertial frames are equivalent. Inertial frames are equivalent in respect to all laws of physics. Well, that is an unprovable statement, because it basically refers to measurements, and we'd have to measure at every possible place, everywhere, to state that. So it's basically a line of dogma. What I'm saying is that those postulates shouldn't be there. We should, if it's true in terms of measurements, we should understand why we get in that scenario through a more holistic theory of, basically God's eye view of the universe and building up from there. So things we bring into our theory things that can't be measured in order to understand things that can be measured. Is that clear? So the speed of light postulate, I mean, that's about a measurement, and that's been defined now as, so it's surplus in the special relativity.
But if I may just interrupt, you appear to be saying that the effects of the two postulates are observed, but they're not maybe inherently true.
They're not fundamental. Yeah, they're just observed. And if you believe all measurements are fundamental and we can only understand the world via measurement, then I think you end up with this utter confusion that we've had for the last 50 years. So all I'm saying is you have to step back, try and take a sort of God's eye view of things as a whole, i.e. real things before they're measured. And then, I mean, all the measurement theory I talked about at the start is all standard stuff. But no one, when you get a book about dimensional analysis, it doesn't have anything about special relativity. And when you get a book about special relativity, it doesn't have anything about dimensional analysis.
All right, James,
and all I'm trying to do
let me interrupt you here.
Is put these two fields together.
Let me interrupt you here. If I'd have known that you were working on this when you first sent me an email, I would have pointed you to my papers at the GSJ, where I have been working on this problem of measurement and relativity and the units of measurement for 20 years. And I could have helped you a whole lot in making this presentation if I'd have known you were going to present this presentation, because I've solved a lot of the problems that you're struggling with already.
All right, you know my email address,
so it's go to the General Science Journal, Harry Ricker. Okay. And what I discovered was that this business about the velocity of light being a constant, what happens is the Lorentz transform changes the units of measurement to always make C a constant. And that's what the Lorentz transform does. It changes the scales of measurement to always make the velocity of light a constant. And that's the secret of the whole thing. Yeah. Okay, I suggest you...
But what I do say is the Lorentz transforms are utter nonsense. Mixing up the space and time doesn't
the way they're interpreted in relativity is correct, is nonsense. And if you go to the GSJ, and I wish you'd contacted me before you did this presentation, because I could have clarified a lot of the questions that you have. I've worked on this for years and years, and I've solved a lot of the problems that you're struggling with. And
but in a nutshell, Harry, would you say that your conclusions are the same as James's? In other words, that there's a fundamental incompatibility between special relativity and dimensional analysis. Are you really saying that?
I'm not really sure that I understand what James is saying. So what I've discovered, or what my theory is that the Lorentz transform changes the units of measurement from one frame to another frame. So in other words, what the Lorentz transform does is it changes the units in which we measure space and time. Okay. Space and time don't change. It just sets different units of measure in different frames of reference. And when those different units are changed, the speed of light is always the same. So according to the standards of measure, the speed of light is always the same, although the units in which the speed of light is measured are different. And that's really kind of a strange idea, isn't it? But that's what the Lorentz transforms do. Now, whether or not you want to accept that as valid physics is another issue.
Yeah, well, I don't accept the Lorentz. Do you accept the Lorentz transforms as they're currently understood or presented?
Not according to, no, because
No.
Einstein misinterpreted the Lorentz transforms. Now, the issue is that the math that they're using in special relativity isn't correct, and the interpretations of the math is incorrect. So what Einstein does is he goes through these Lorentz transforms and then solves an equation, and he says, oh, look here, this time that I solved shows that the time has changed on the clocks. The time has changed on the clocks. He does this in 1905. And then he says, well, time has changed. He didn't say the clock changed. He says time has changed. There was no reason for him to say that, other than he assumed at the beginning that all clocks are calibrated to the same time.
Yeah, this is this problem with the twin paradox.
But he never recognized that clock in motion.
This is the problem with the twin paradox.
And I'm going to have to be very rude now. I think there's a lot of
okay. I'm sorry, I talked too fast.
The two of you. I mean, we might have a minute more. I want to bring in somebody else and maybe bring in some summary, but
all right, I think I'm just recommending that we talk more on this.
But I also see differences, and I think there's a lot more to discuss between you two gentlemen. We might be able to do that.
The trouble is that conceptual things take surprisingly long time to twig, and you may have a different conceptual structure to me. So, and it's quite hard sometimes to work out where people are coming from. So we'll aim to do that maybe in the future in the most efficient way. Yeah, all I can do is try and increasingly trying to clarify what we're trying to say so other people can understand and respond. I mean, that's basically what science is, isn't it?
And I mean, sometimes we do engage in not a protracted email correspondence, but maybe after a lecture, we might have one or two emails just going back and forth, just saying, look, you said A, was it such and such, was it B? It doesn't get you into a long, never-ending email. But if there's anything inconsistent there, or, for example, you, James, might look up the General Science Journal under Harry Ricker and some of those papers.
I have got a lot of his papers because I was looking at the ones relative to Dingle. Okay. But I'm not quite sure whether those were the ones you're talking about.
Well, if you want to be more specific, Harry, giving a pointer.
Go to the second page and go to the second page. Go to the second page. The ones on Dingle kind of touch on this whole thing. Dingle made the point that what was wrong with special relativity was it didn't have a good, precise definition of time because time is defined relative to a standard. Okay. And that was his big objection to special relativity, that the definition of time was not clear in special relativity because it had to be defined relative to a standard. Okay. Now it turns out
between the two approaches, all right.
But I think some work has to be done to make this
most of what he referenced. Well, I didn't realize when we first exchanged emails that you were interested in this topic, because I'd pretty much solved the.
And actually, I'm forgetting, you pardon me, but I'm forgetting that you were in touch with each other. And in fact, Harry introduced me to James. I've completely forgot about that. I thought you were coming anew to it. So that I understand that. Anyway, so at least you have the contacts of each other. And, I'd value any input, and maybe even copy me on some of this would be interesting. So if I may just bring Harry down, and thank you very much for your contribution.
Thank you, Harry.
Just we have a minute or two. Cornelius, I think I frightened Eric away because he's gone now when I said put your camera on, but he's put his camera on. So if you want to say, I know you made a comment, Cornelius, if you want to make just one brief comment, we can maybe address it before closing down.
Well, I was just commenting basically on the acceleration part, because James brought up the idea that the ballistic theory worked with MMX, but the ballistic theory actually does have acceleration as it reflects off the mirrors and that. And so if you're changing speeds and directions, that's acceleration. So you're moving into explaining it then through general relativity rather than just special relativity. And in my view, it's kind of like Harry said, basically, the theory is based on the constancy of speed of light. And that's basically a postulate is not a fact. It is an assumed fact, assumed condition under which the rest of your theory is written around. So the mathematics was supposed to have been written around the idea that light is your constant, light is your measurement standard, and therefore everything else was based on that. So because of that, distance has changed, times appear to change, but it's because of it's a chosen standard. That's, in my understanding, that's what a postulate is, and it's just a chosen method of measuring it. If you look at mechanical standards and use a mechanical standard of light, measuring the speed of light, you'll see that obviously light, as it goes through a piece of glass, will change speeds, because we see it going into the glass and we see it going out of the glass. We don't exist within the glass, so we can't see that within the glass under the conditions of the glass, where it has to go in and out of the molecules and in and out of the atoms, that it's actually had to change distances and that in order to go through that glass, because it's not a straight line anymore. It's like traveling across the surface of the So
that's the
any brief response to that, James?
That's the gravitation, because I haven't referred to that, but basically, gravity is like a refractive index medium for light, effectively, and so that's in the background there, and obviously that needs to be incorporated into these ideas. If it's to be taken seriously as a more general theory, but you can only start somewhere. So I accept exactly what you're saying. There's more work to do.
That's kind of where Einstein started with the special theory of relativity. He's starting somewhere, but he didn't take into account all the acceleration and gravity characteristics. So
and he tried to do that later with the general.
Yeah. And you can't really separate the two and get a full picture.
Right.
I agree. You have to do it all at once, I think. And otherwise you end up with a complicated set of bit theories that somehow fit together, but no one quite knows how, which is what we've got now.
Probably. Well, thanks very much, Cornelius.
Thank you.
For that contribution. Sorry it was so brief. And so let me just get back to the original form, and I'll just fulfill my pleasurable duty of thanking James very much for again giving us the benefit of his analysis. He's done a lot of work in preparing all those slides, a lot of material in them. I know, small writing and so on, but he went through them and his contention. I think maybe personally I'm getting a bit of a light now from what Harry said, with regard to the Lorentz transformation and discussing that with James. I'm getting a sort of a light with regard to the commonality between the two. If one feels that just by listening to this lecture, you'd say, "Oh goodness me, here's another complete conflict with special relativity." One might be disappointed. One mightn't be convinced. One might say, "Well, there is some inconsistency there," and but James has been very lucid in explaining to us the possible inconsistency there, and maybe the lack of thinking this out thoroughly on the part of people who sort of rushed to ideas, Einstein and maybe Minkowski and so on. So there is a lot more which we need to address here. And as I say, I haven't finalized this with James yet, but we are hoping to bring him back once again, which will be the third time in a short period of time that he'll be speaking to us. And it'll be on deriving the classical Newtonian gravitational law from effectively first principles. Now, unfortunately, we have, or fortunately, perhaps I should say, we have, we're bespoke now for the next 2 months or so. So I think it'll be in October that we'll be seeing James again. Although I hope he'll participate, in some of our conferences in the meantime. And we're hoping to revert actually to time dilation and maybe looking at this whole business of light clock and two-way speed of light and so on next week, or next fortnight rather. But so keep an eye on the announcements, because it won't be verified until then, but it is down on our roster. So again, it is my great pleasure to be able to thank James very much for having taken the trouble of coming, addressing all the questions, answering them in a very manful way, but both in the social media and also the direct ones that have been posed to us. And I'm sorry, we really didn't have enough time. I mean, certainly the points raised by Denny, by James, and by Harry, and also by Cornelius, could have led us into a discussion for a half hour in each case at least. And we just didn't have that time. But that indicates the importance of the subject. And I think certainly for my own part, it's spurred in my mind a desire to look at this question of dimensional analysis and measurement further. I think James even jocularly said that I had worked in the Standards Authority in my former life, and we dealt with metrology, among other things. So it's an area that isn't totally foreign to me. So once again, just a few minutes over the time. I don't think we're going to be cut off quite yet, but I'd like to thank you all sincerely for having participated today. You're a very loyal group. I see a lot of common names coming up on the social media, and you're all engaging in great discussions between yourselves, and frequently we don't need to answer them because they're just one-to-one correspondences, and that's great. It shows that there's a great vibrancy in these technical sessions. And I'd like to thank especially all of you in the green room for having taken the trouble of coming in directly and addressing the points and giving us a more detailed analysis of what was being said by the speaker. We're critical thinkers, so we'll be critical not only of the mainstream, we'll be critical of each other, and that's all to be desired. And last but not least, of course, I must thank our speaker, James Arathoon. I've only known James for some time now, but I found him most stimulating in all the areas he's looked at. I've actually looked at this business of the conductivity of the atmosphere and so on. I've had a quick look at that on the internet, and I found it most illuminating. So I know he's a thinker of moment, and I certainly would value his next presentation to us. And I'm certainly very glad that we have now, for all time, a record of on YouTube of the two presentations from James. And you can go back and look at them, again, and give us further thoughts that didn't occur to you at the time they were presented. That would be quite fine. So I'm going to close the session now, and thanking you all, and James in particular. And wherever you are in the world, I'm going to wish you a very good day. And we're having extremes of weather, either a lot of rain here in this part of the world, or extreme heat in other parts. So I'll wish you farewell and a very good day. End of broadcast now.